November 3rd, 1943. Somewhere over the Solomon Islands, the metallic screech of torn aluminum pierced the tropical air as Ensign Joseph Farnsworth's F6F-3 Hellcat, Bureau number 08742, shuddered violently under the impact of 20mm cannon fire. The young pilot from Fighting Squadron 5 had been caught in a climbing turn by a pair of Mitsubishi A6M0 fighters, their experienced pilots, exploiting the single moment when Farnsworth had allowed his airspeed to bleed off too much during aggressive maneuvering over Bougainville. His Pratt Whitney R-2800 double wasp engine, that massive 18-cylinder power plant producing 2,000 horsepower, began streaming thick black smoke from penetrated cylinders. Oil pressure dropped precipitously as vital fluids sprayed from ruptured lines. Farnsworth knew immediately that he would not make it back to the carrier Enterprise, steaming somewhere beyond the horizon to the southeast. The Hellcat, bearing the distinctive white number 13 on its fuselage and the geometric tail markings of Air Group 5, began losing altitude despite Farnsworth's best efforts to nurse the dying engine. He had perhaps 5 minutes before catastrophic failure would force him to bail out over enemy-controlled territory or attempt a desperate landing somewhere in the Japanese-held islands below. Through the smoke and confusion, Farnsworth spotted what appeared to be a partially cleared area on the northern coast of Bougainville Island, near Japanese-controlled territory. It was not much, barely 500 yards of reasonably flat ground, but it represented his only chance. He shut down the engine before it could seize completely and tear itself from its mounts, trimmed the Hellcat for best glide ratio, and committed to the landing. The approach was marginal at best. Farnsworth managed to drop his landing gear at the last moment, the hydraulic system still functioning despite the battle damage. The Hellcat struck the rough ground hard, bounced violently, then settled onto all 3 wheels as Farnsworth stood on the brakes. The fighter rolled to a stop less than 50 yards from the tree line, its propeller blades bent from ground contact, its engine destroyed, but its airframe remarkably intact considering the violence of the combat and the emergency landing. Farnsworth unstrapped quickly, knowing Japanese ground forces would reach the crash site within minutes or hours at most. He had been briefed on survival procedures, on what to do if forced down in enemy territory. But as he climbed from the cockpit and prepared to flee into the jungle, he heard voices shouting in Japanese, much closer than he had anticipated. A patrol had been nearby, drawn by the sound of the crash. Within moments, Japanese soldiers emerged from the tree line, weapons raised. Farnsworth raised his hands in surrender, his war over before it had barely begun. But for his aircraft, Bureau number 08742, an extraordinary second life was just beginning. This Hellcat would soon be transported across the Pacific to Japan itself, where it would undergo the most thorough examination any American fighter had yet received from Japanese engineers and test pilots. What they would discover in that examination would profoundly disturb the assumptions held by some of Japan's most experienced aviation designers and would force painful acknowledgement of how far Japanese fighter development had fallen behind American engineering capabilities. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how captured American aircraft became instruments of revelation for Japanese engineers begins not with Farnsworth's forced landing on Bougainville, but with Japan's escalating crisis in the Pacific Air War and the desperate need for accurate intelligence about American aircraft capabilities that went beyond fragmentary combat reports and propaganda-distorted assessments of enemy strength. By late 1943, the Imperial Japanese Navy faced a strategic situation that had deteriorated dramatically from the heady days of early 1942, when Japanese aviation had dominated Pacific skies. American industrial production was delivering new aircraft in quantities that seemed almost impossible to Japanese observers, accustomed to their own limited manufacturing capabilities. American pilot training programs were producing thousands of new aviators, while Japanese training had been severely curtailed by fuel shortages and the loss of experienced instructors to combat attrition. Most troubling of all, American aircraft had improved dramatically in performance and capability. The fighters that had struggled against the Zero in 1942 had been replaced by new types that matched or exceeded Japanese aircraft in most, Critical performance categories. Intelligence reports from combat pilots provided fragmentary accounts of these new American fighters, but these reports often conflicted with one another and reflected the chaos of combat rather than systematic, controlled analysis. Japanese aviation commanders understood they needed more than scattered combat reports to counter the American threat effectively. They required detailed technical intelligence about American aircraft construction, systematic evaluation of performance capabilities, and careful analysis of design philosophy to understand how American engineers approached the fundamental problems of fighter design. The concept of testing captured aircraft was not new. Both the Allies and Japanese had examined enemy machines throughout the war. But Japanese efforts had been hampered by several factors that limited the value of captured aircraft intelligence. First, relatively few American aircraft had been captured intact enough for meaningful testing. American pilots generally destroyed their aircraft when forced to land in enemy territory, or battle damage was so severe that repair proved impossible with available resources. Second, Japanese facilities for testing captured aircraft were limited compared to the extensive German programs in Europe. The Technical Aeronautics Research Institute at Tachikawa and the Naval Air Technical Arsenal at Yokosuka conducted evaluations, but resources remained constrained by Japan's overall industrial limitations. Third, and perhaps most importantly, a prevailing attitude among some Japanese military leaders and engineers held that American aircraft represented crude, mass-produced machines that could teach little to Japanese designers who had created the Zero, widely considered in 1942 to be the world's finest carrier fighter. This comfortable assumption would be systematically demolished by careful examination of Farnsworth's Hellcat. The recovery operation for American aircraft on Bougainville required significant effort under difficult circumstances. Japanese ground forces controlled much of the island, but Allied air superiority meant that any large-scale transportation of equipment risked attack from American fighters and bombers operating from newly captured airfields in the region. Nonetheless, Japanese commanders recognized the extraordinary value of capturing an intact example of the F6F Hellcat, about which Japanese intelligence knew relatively little beyond basic performance estimates derived from combat observations. Within days of Farnsworth's forced landing, specialized Japanese salvage personnel reached the crash site. They examined the Hellcat carefully, noting with professional interest that despite battle damage and the emergency landing, the airframe remained structurally sound. The combat damage was extensive but localized, affecting primarily the engine and some forward fuselage components. The wings, tail surfaces, landing gear, and most importantly, the overall airframe structure appeared repairable with available resources. The decision was made to attempt recovery and transport to Japan for detailed evaluation. This required dismantling the aircraft sufficiently to allow transportation by ship, a delicate operation that had to preserve as much of the original configuration as possible for later reassembly and testing. Japanese technicians worked methodically, photographing and documenting every step of the disassembly process to ensure proper reassembly later. The Hellcat's massive R-2800 engine, even in its damaged state, impressed the Japanese salvage team immediately. The sheer size of the 18-cylinder radial engine dwarfed anything in Japanese service. The Nakajima Sakai engine that powered the Zero produced 950 horsepower. The Mitsubishi Kase engines in later Zero variants and in aircraft like the J-2M Raiden produced between 1400 and 1800 horsepower, depending on the specific model. But this American engine, the Pratt Whitney R-2800 Double Wasp, was rated at 2000 horsepower, a figure that seemed almost excessive to engineers accustomed to Japanese design philosophy, emphasizing lightweight construction and fuel efficiency over raw power. By late November 1943, the disassembled Hellcat had been carefully loaded onto a cargo vessel for transportation to Japan. The voyage required careful routing to avoid areas where American submarines operated with increasing effectiveness against Japanese shipping. Several weeks later, the components arrived at Yokosuka Naval Air Technical Arsenal, located on Tokyo Bay approximately 30 miles south of the capital. Yokosuka served as one of Japan's primary naval aviation research and testing facilities, equipped with workshops, test stands, wind tunnels, and other specialized equipment necessary for thorough aircraft evaluation. The facility had examined captured Allied aircraft before, including examples of the P-40 Warhawk, F4F Wildcat, and various British types. But the F6F Hellcat represented something new, a fighter specifically designed to counter the Zero and dominate Pacific air combat. The reassembly and repair process began immediately under the direction of experienced engineers and technicians who understood both the technical challenges and the strategic importance of the project. The damaged R-2800 engine could not be repaired to full operational status with available resources, lacking replacement cylinders manufactured to proper specifications and tolerances. However, engineers could examine the engine in extraordinary detail, measuring every component, analyzing materials, studying the supercharger system, and attempting to understand the design philosophy that had created such a powerful and reliable power plant. The airframe received meticulous attention. Every structural component was examined, measured, and analyzed. Engineers studied the wing design, noting the relatively thick airfoil section, quite different from the thin, highly cambered wings of the Zero. They examined the control surfaces, discovering hydraulic boost systems that assisted the pilot in moving ailerons and elevators, systems that added weight but provided full control authority at all speeds. The landing gear impressed Japanese engineers with its robust construction. The main gear struts were massively built compared to Japanese practice, capable of absorbing hard carrier landings that would have collapsed lighter landing gear designs. The tail wheel was fully retractable, a feature the Zero lacked, reducing drag in flight at the cost of additional weight and mechanical complexity. The cockpit revealed a design philosophy fundamentally different from Japanese fighters. The pilot's seat featured substantial armor plate protection behind and below, weighing many pounds, but providing crucial protection against enemy fire from the faced rear hemisphere. The instrument panel was comprehensive, with clearly marked gauges for every critical system, arranged logically for quick reference during the stress of combat operations. Visibility from the raised cockpit position exceeded anything in Japanese service. The pilot sat high in the fuselage with excellent views forward, to the sides, and even somewhat to the rear despite the turtleback fuselage design. Japanese engineers noted that this raised position added weight and increased fuselage cross-section, creating additional drag, but the tactical advantage of superior visibility clearly outweighed these penalties in American design thinking. The fuel system incorporated self-sealing tanks, a technology Japanese aircraft lacked throughout most of the war. These tanks used multiple layers of rubber compounds that would swell when punctured by bullets or shell fragments, automatically sealing small holes and preventing catastrophic fuel loss and fire. The system added significant weight, approximately 200 pounds compared to standard tanks, but dramatically improved aircraft survivability when hit by enemy fire. Japanese engineers examined these self-sealing tanks with particular interest, recognizing immediately that this represented a fundamental difference in design philosophy. The Zero had been designed for maximum performance through minimum weight, accepting vulnerability to battle damage as the price for superior maneuverability and range. The Hellcat accepted substantial weight penalties for protection, armor, and robust construction, compensating for these penalties with overwhelming engine power. The armament package consisted of 6 50-caliber M2 Browning machine guns, all mounted in the wings with ammunition boxes positioned inboard of the guns. This concentration of firepower could deliver approximately 5,000 rounds per minute combined rate of fire during the brief moments when all 6 guns fired simultaneously. The ammunition capacity allowed approximately 20 seconds of sustained fire, more than adequate for most combat engagements where firing opportunities lasted only a few seconds. Japanese engineers noted that each of these 50-caliber machine guns weighed approximately 65 pounds empty, with ammunition adding substantial additional weight. The 6 guns, plus ammunition, mounting hardware, and feed systems, added over 1,000 pounds to the Hellcat's empty weight. The Zero, by comparison, carried 2 7.7mm machine guns and 2 20mm cannons, a lighter but potentially more devastating armament package when the cannons connected with their target. The structural analysis revealed construction that emphasized durability over minimum weight. The Hellcat's airframe used substantially thicker aluminum alloy sections than Japanese practice throughout primary load-bearing structures. Stringers and longerons were more numerous and more robust than the minimum, required by theoretical stress analysis. Redundant load paths ensured that if one structural member failed, others could carry the loads, preventing catastrophic structural failure from battle damage. This design philosophy reflected American engineering culture that valued reliability and damage tolerance, accepting weight penalties for the assurance that aircraft would survive combat damage and rough handling by pilots with varying skill levels. Japanese engineering, constrained by limited industrial capacity and strategic material shortages, had optimized for minimum weight, creating aircraft that performed beautifully when undamaged, but proved fragile when hit or mishandled. One Japanese engineer examining the Hellcat structure later wrote in his technical report that the aircraft appeared to be built with twice the necessary strength, a criticism from the perspective of weight optimization, but an acknowledgement of American design philosophy that prioritized survivability. He noted that a Zero airframe of equivalent strength would weigh perhaps 2,000 pounds more than the actual Zero, making it too heavy to fly with available Japanese engines. The engine examination provided the most sobering revelations for Japanese engineers who understood powerplant technology. The Pratt Whitney R-2800 double WASP represented a level of engineering, sophistication, and manufacturing capability that Japan could not match with existing industrial resources and technical knowledge. The engine displaced 2,800 cubic inches, hence its designation, compared to the Nakajima Sakai's 1,500 cubic inches, and even the larger Mitsubishi Kasei's 1,800 cubic inches. But displacement alone did not explain the enormous power output. The R-2800 achieved its 2,000 horsepower through multiple advanced technologies that Japanese engine designers understood theoretically but could not replicate practically. The two-stage supercharger system maintained sea-level manifold pressure to much higher altitudes than Japanese single-stage systems, allowing the engine to produce maximum power well above 20,000 feet, where Japanese engines gasped for air. The internal construction revealed manufacturing precision that impressed Japanese engineers, despite their recognition that such precision remained beyond Japan's industrial capabilities. Cylinder barrels were machined to tolerances measured in thousandths of an inch, then fitted with steel cylinder liners that provided excellent wear resistance. Piston rings seated perfectly, minimizing blow-by and maximizing compression efficiency. Connecting rods were forged from high-grade alloy steel, then precision machined to exact weight specifications, so that all 18 cylinders operated in perfect balance. The lubrication system incorporated pressurized oil delivery to every bearing surface, ensuring adequate lubrication even during violent combat. Maneuvers involving high acceleration forces. Japanese engines used simpler lubrication systems that sometimes proved inadequate during sustained hard maneuvering, leading to bearing failures and engine seizures that forced pilots to land immediately or bail out. Materials analysis revealed American access to strategic alloys that Japan increasingly lacked. High-grade aluminum alloys provided excellent strength-to-weight ratios throughout the airframe. Specialized steel alloys with precise metallurgical properties were used in highly stressed components. Rubber compounds for seals, hoses, and self-sealing fuel tanks maintained their properties across wide temperature ranges, from tropical heat to high-altitude cold. Japan faced severe shortages of these strategic materials by late 1943. Aluminum supplies, never abundant, had become critically scarce as Allied submarines and aircraft interdicted shipping routes from resource-rich territories in Southeast Asia. High-grade, steel-required alloys that Japan could not produce domestically in sufficient quantities. Rubber was perhaps the most critical shortage, forcing the use of inferior substitutes that degraded quickly in service. The technical evaluation team at Yokosuka produced a comprehensive report documenting their findings. The report, classified as highly secret and distributed only to senior naval aviation commanders and design bureau chiefs, made uncomfortable reading for those who had believed Japanese aviation maintained technical parity with American developments. The report detailed the Hellcat's specifications. Empty weight approximately 9,300 pounds, loaded weight approximately 12,500 pounds for typical combat configuration, maximum speed approximately 375 miles per hour at optimal altitude, service ceiling approximately 37,000 feet, combat radius approximately 300 miles with standard fuel load, armament consisting of 6 50-caliber machine guns with 1,900 rounds total ammunition. More important than the raw specifications were the conclusions the evaluation team drew about American design philosophy and industrial capabilities. The report noted that the Hellcat represented a fundamentally different approach to fighter design than the Zero, accepting substantial weight penalties for protection, firepower, and structural ruggedness, then compensating for these penalties with overwhelming engine power that Japan could not match. The report emphasized that the R-2800 engine alone weighed approximately 2,400 pounds, nearly as much as an entire Zero fighter. This single component represented a level of industrial capability that Japan could not replicate. American industry could produce engines of this size, complexity, and power output in large quantities with consistent quality. Japanese industry struggled to produce the smaller, simpler engines that powered current Japanese fighters. The implications extended beyond simple technical comparison. The Hellcat demonstrated that American engineers had solved the fundamental challenge of carrier fighter design by brute force. Where Japanese designers had optimized for minimum weight to achieve acceptable performance with limited engine power, American designers had simply installed an engine so powerful that weight penalties for protection and armament became acceptable. This represented a philosophical divide that reflected broader differences in industrial capacity and strategic resources. Japan, with limited manufacturing capability and constrained access to strategic materials, had no choice but to optimize obsessively for minimum weight. America, with vast industrial capacity and abundant resources, could afford to build fighters that weighed twice as much as their Japanese counterparts, compensating for the weight penalty with engines that produced more than double the horsepower. The Yokosuka evaluation team attempted to recommend design improvements for future Japanese fighters based on lessons learned from the captured Hellcat. These recommendations included developing higher-powered engines, incorporating pilot armor and self-sealing fuel tanks, strengthening airframe structures to improve survivability, and improving high-altitude performance through better supercharger systems. However, the engineers understood that these recommendations, while technically sound, were practically impossible to implement given Japan's deteriorating industrial situation and severe resource constraints. Developing a 2,000-horsepower engine would require years of research and development that Japan no longer had. Incorporating armor and self-sealing tanks would require strategic materials that were increasingly unavailable. Strengthening airframes would reduce production rates at a time when quantity had become as critical as quality. The captured Hellcat thus served primarily as an intelligence tool, revealing the scale of American advantages rather than providing practical solutions Japanese designers could implement. This uncomfortable knowledge spread through Japanese naval aviation circles as senior officers and engineers read the classified reports and understood the implications. Some Japanese test pilots were given the opportunity to examine the captured Hellcat closely, sitting in the cockpit, studying the controls and instruments, and imagining what it would be like to fly such a machine. Though the damaged engine prevented actual test flights, ground runs were conducted to evaluate engine operation and systems functionality with repaired components. Lieutenant Saburo Sakai, one of Japan's highest-scoring aces with over 60 confirmed victories, visited Yokosuka in early 1944 and examined the captured Hellcat carefully. Years after the war, Sakai would write about his impressions of the American fighter, noting particularly the substantial armor protection, the robust construction throughout the airframe, and the sheer size of the engine installation. Sakai recognized immediately that American pilots flying Hellcats enjoyed protection he had never experienced in the Zero. The armor plate behind the seat would stop most machine gun rounds and many cannon shells from the rear hemisphere. The self-sealing fuel tanks would prevent the catastrophic fires that had killed so many Japanese pilots when fuel tanks were punctured. The rugged construction would allow the aircraft to absorb battle damage and still return to base. He understood with uncomfortable clarity that his survival through dozens of combat missions had depended partly on skill and experience, but also substantially on luck. He had been shot down twice, severely wounded once, and survived encounters that would have been fatal if his Zero had caught fire or broken up from battle damage. American pilots in Hellcats would survive situations that killed Japanese pilots in Zeros, a simple matter of engineering philosophy and industrial capability. Other experienced Japanese pilots who examined the captured Hellcat came to similar conclusions. The aircraft represented a different design paradigm, one that prioritized pilot survival and operational effectiveness over pure performance metrics. This philosophy made sense for America, which could train thousands of new pilots annually and needed to keep them alive to develop experience. It made less sense for Japan, which faced severe pilot training limitations and needed maximum performance from limited resources. But the luxury of choosing design philosophy had become irrelevant by 1944. Japan was losing the air war not because of design philosophy choices, but because American industry could produce overwhelming numbers of fighters that were both well-protected and high-performing, while Japanese industry struggled to produce sufficient aircraft of any type. The examination of the Hellcat's construction methods revealed manufacturing techniques that enabled true mass production while maintaining quality. The airframe was designed for modular construction, with major assemblies built separately, then joined during final assembly. This allowed parallel manufacturing streams that maximized production efficiency. Standardized components were used throughout, reducing the number of unique parts that had to be manufactured and simplifying logistics for spare parts. Riveting patterns were optimized for strength while minimizing manufacturing time. Access panels were positioned to facilitate rapid inspection and maintenance in field conditions. Japanese engineers recognized these features as evidence of design for manufacturing philosophy, where production considerations were integrated into the design process from the beginning rather than treated as afterthoughts. American designers understood that an aircraft design, however sophisticated, was worthless unless it could be manufactured in quantity with consistent quality. This represented another philosophical difference between American and Japanese approaches. Japanese aircraft design often prioritized absolute performance over manufacturing ease, resulting in aircraft that were difficult and time-consuming to produce, even under optimal conditions. The Zero itself, despite its lightweight construction, required skilled labor and careful assembly to achieve proper flight characteristics. American designs increasingly emphasized manufacturing efficiency, recognizing that producing 100 good fighters was more valuable strategically than producing 50 excellent fighters. This philosophy, combined with American industrial might, created the overwhelming numerical superiority that Japanese forces faced by 1944. The Yokosuka Evaluation Team's report included detailed photographs of every aspect of the Hellcat's construction, providing visual documentation that supplemented the written technical analysis. These photographs circulated among Japanese aircraft designers, offering insights into American construction techniques and design solutions for various engineering challenges. One photograph showed the Hellcat's main landing gear attachment points, revealing massive forged fittings that distributed loads into multiple airframe members. Japanese engineers noted that these fittings alone probably weighed more than an entire Zero landing gear assembly. But they understood the reasoning. The robust construction ensured reliability during thousands of carrier landings, while lighter Japanese gear sometimes failed under the stress of hard landings on carrier decks. Another photograph documented the Hellcat's wing fold mechanism, which allowed the outer wing panels to fold upward for compact storage on carrier hangar decks. The mechanism was purely mechanical, requiring no hydraulic systems, operated by deck crews using hand cranks. Japanese engineers appreciated the elegant simplicity of the design, which achieved the necessary function with minimum complexity and maximum reliability. The fuel system photographs revealed the sophisticated plumbing required for self-sealing tanks, with multiple fuel cells interconnected to ensure continued fuel flow even if some cells were damaged. Fuel pumps, filters, and valves were positioned for easy access and replacement. The entire system was designed for maintainability, recognizing that complex systems required regular servicing and occasional repairs. Japanese aircraft fuel systems tended toward simplicity bordering on crudeness, with minimal redundancy and limited serviceability. This reflected both design philosophy and resource constraints. Simpler systems weighed less and required fewer strategic materials to manufacture, but they proved less reliable in service and more vulnerable to battle damage. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By mid-1944, the intelligence gathered from the captured Hellcat had been thoroughly disseminated throughout Japanese naval aviation circles. Senior commanders understood the technical challenges they faced. Design Bureau engineers recognized that American aircraft had surpassed Japanese designs in most critical performance categories. Experienced pilots knew they would face opponents flying superior aircraft with better protection and overwhelming numerical advantage. This knowledge, while professionally valuable, could not overcome the fundamental disadvantages Japanese forces confronted. Understanding that American fighters were technically superior did not help Japanese pilots flying inferior aircraft win dogfights. Recognizing that American engines produced twice the horsepower of Japanese engines did not enable Japanese industry to manufacture comparable power plants. Knowing that American pilots enjoyed armor protection and self-sealing fuel tanks did not protect Japanese pilots flying vulnerable Zeros. The captured Hellcat became a symbol of American industrial and technical superiority, a tangible demonstration that Japan faced opponents with decisive advantages in every dimension of the air war. Some Japanese engineers and officers drew the logical conclusion from this evidence. The war was unwinnable, and continued fighting would only increase the ultimate cost of inevitable defeat. Others clung to hopes that superior fighting spirit, tactical innovation, or new weapons under development might somehow offset American material advantages. The Mitsubishi J-2M Raiden and Kawanishi N-1KJ Shiden represented attempts to create fighters that could compete with the Hellcat on more equal terms. But both programs faced severe difficulties with engine reliability, manufacturing delays, and resource shortages that prevented them from entering service in meaningful numbers. The most advanced Japanese fighter project, the Mitsubishi A-7M Reppu, intended as the Zero's successor, promised performance comparable to the Hellcat through refined aerodynamics and a more powerful engine. But development delays and changing requirements meant the first prototype did not fly until May 1944, and only 8 examples were completed before war's end. The Reppu never saw combat, remaining a promise unfulfilled. Japan's aviation industry, which had seemed formidable in 1941 and 1942, was collapsing under multiple pressures by 1944. American submarine warfare had severed shipping routes carrying strategic materials from Southeast Asian territories. American strategic bombing was beginning to target aircraft factories and component manufacturers. Most critically, the training pipeline that produced skilled workers for aircraft manufacturing had been disrupted by military conscription that drafted experienced technicians into combat units. Aircraft production actually peaked in mid-1944, with over 28,000 aircraft manufactured that year, but quality declined precipitously as skilled workers were replaced by hastily trained substitutes and elderly workers recalled from retirement. Engines suffered from inadequate quality control, with cylinder barrels machined to improper tolerances, piston rings that did not seat correctly, and bearings that failed prematurely. Airframes exhibited manufacturing defects that degraded performance and sometimes caused structural failures. The contrast with American production could not have been starker. American aircraft factories were producing over 96,000 aircraft in 1944, more than triple Japanese output, while maintaining or improving quality standards. The Grumman factory at Bethpage, Long Island, was producing F6F Hellcats at peak rates exceeding 600 per month from a single facility, more than all Japanese naval fighter production combined. These production figures were well known to Japanese intelligence through various sources, but they seemed almost incomprehensible to officers accustomed to Japan's limited industrial base. How could one American factory outproduce all of Japan's aircraft manufacturers combined? The answer lay in American industrial organization, abundant resources, sophisticated machine tools, and an enormous trained workforce that Japan simply could not match. The captured Hellcat thus served as both intelligence source and psychological weapon, demonstrating American superiority in ways that affected Japanese morale across all levels of naval aviation. Pilots understood they flew inferior aircraft against superior opponents. Ground crews recognized that American aircraft they sometimes encountered after battles exhibited better quality construction than Japanese machines they serviced daily. Engineers knew that American design and manufacturing capabilities exceeded Japanese achievements in nearly every measurable category. This demoralization contributed to declining combat effectiveness as the war progressed. Japanese pilots who had begun the war confident in their training, their aircraft, and their tactical doctrines faced opponents in late 1944 who possessed advantages in every dimension: better aircraft, more thorough training, superior tactics, overwhelming numbers, and comprehensive logistics support. Combat reports from Japanese pilots during this period reflect increasing desperation. Encounters with formations of Hellcats typically resulted in severe Japanese losses for minimal American casualties. The tactical disadvantages were simply too great to overcome through courage or tactical skill. American fighter pilots had developed tactics specifically optimized for the Hellcat's strengths, using high-speed slashing attacks that exploited superior speed and climb rate, while avoiding slow-speed turning fights where Japanese fighters retained some advantage. The Thuch-weave defensive tactic, developed earlier in the war, had been perfected and standardized, providing effective mutual support between wingmen that negated the Zero's superior maneuverability. Most importantly, American pilots fought as teams, with wingmen covering each other and refusing to be drawn into individual dogfights. Japanese pilots, trained in individual combat techniques and fighting increasingly alone as formation discipline broke down under American numerical superiority, found themselves outnumbered and outmaneuvered by coordinated American tactics. The Battle of the Philippine Sea in June 1944 demonstrated the complete transformation of the Pacific Air War. Japanese carrier aviation, painstakingly rebuilt after devastating losses at Midway, was effectively annihilated in a single day of combat that became known as the Great Marianas Turkey Shoot, American F6F. Hellcats shot down over 300 Japanese aircraft for the loss of fewer than 30 American planes, a kill ratio exceeding 10-1. Japanese pilots and commanders who survived the Philippine Sea understood with absolute clarity that they faced opponents with overwhelming advantages that could not be overcome. The captured Hellcat, examined at Yokosuka, represented in microcosm the broader disparity between Japanese and American capabilities. Every technical advantage the Hellcat possessed translated directly into tactical superiority in combat. As the war entered its final year, the captured Hellcat remained at Yokosuka, occasionally examined by engineers working on new aircraft projects, but increasingly irrelevant as Japan's strategic situation deteriorated beyond any possibility of technological salvation. The aircraft survived American air raids that increasingly targeted Japanese military installations, perhaps through luck or perhaps because American intelligence knew of its presence and wanted it preserved. When American occupation forces entered Yokosuka Naval Arsenal in September 1945 after Japan's surrender, they discovered the captured Hellcat still present, now bearing Japanese markings and identification codes painted over its original American insignia. The aircraft was carefully documented, photographed extensively, then evaluated to determine whether it should be preserved or scrapped. Ultimately, the decision was made to scrap the airframe, as dozens of airworthy Hellcats remained in American service, and the captured example offered no particular historical value worth the expense of preservation and shipment back to the United States. The aircraft that had provided such valuable intelligence to Japanese engineers was cut up and recycled, its aluminum returned to industrial use in post-war reconstruction. Ensign Joseph Farnsworth, whose forced landing on Bougainville had inadvertently provided this intelligence windfall to Japanese forces, survived the war as a prisoner. He was captured by Japanese forces immediately after his crash, spent the remainder of the war in various POW camps in the Pacific, and was repatriated in September 1945 after Japan's surrender. He returned to the United States, resumed civilian life, and rarely spoke about his wartime experiences or the fate of his aircraft. The irony of the situation would not have been lost on those familiar with the full story. An American aircraft captured by Japanese forces provided detailed intelligence about American technical capabilities, but that intelligence proved useless because Japan lacked the industrial capacity and resources to implement the lessons learned. The captured Hellcat revealed what Japanese engineers already suspected. American aircraft were technically superior in most critical respects, and this superiority reflected broader American advantages in industrial capacity, technical education, resource access, and manufacturing sophistication. The Japanese engineering community's response to the captured Hellcat reflected a complex mixture of professional admiration and strategic despair. Engineers appreciated the sophisticated design and robust construction, recognizing the Hellcat as an excellent example of its type. But they understood that Japanese industry could not replicate these achievements without fundamental transformations in manufacturing capability, resource availability, and technical knowledge that were impossible to achieve during wartime. Some Japanese engineers who examined the Hellcat carefully later wrote about their experiences, describing both the technical insights gained and the psychological impact of understanding how completely American aviation had surpassed Japanese capabilities. These accounts, published decades after the war, when veterans could speak more freely about their experiences, provide valuable historical perspective on how Japanese aviation professionals viewed their American counterparts. One such account described the massive R-2800 engine as a monument to American industrial power, noting that the engine alone represented a level of manufacturing sophistication that Japan had never achieved. The precision machining, the sophisticated supercharger system, the reliable operation under extreme conditions, all reflected engineering excellence and manufacturing capability that Japanese industry could not match. Another engineer focused on the Hellcat's protection systems, describing the armor plate, self-sealing fuel tanks, and robust structure as evidence of American design philosophy that valued pilot survival as highly as aircraft performance. He contrasted this with Japanese design philosophy that had sacrificed protection for performance, accepting high pilot casualties as the price for superior maneuverability and range. This fundamental difference in design philosophy reflected deeper cultural and strategic differences between American and Japanese approaches to warfare. American forces, with enormous manpower reserves and sophisticated training programs, could afford to protect their pilots and aircraft, recognizing that experienced pilots were valuable assets worth preserving. Japanese forces, with limited manpower and constrained training capacity, had designed aircraft to maximize performance regardless of survivability, accepting casualties as inevitable. The long-term consequences of these different philosophies became apparent as the war progressed. American squadrons maintained experience levels because pilots survived combat encounters, learned from their experiences, and passed knowledge to newer pilots. Japanese squadrons saw experience levels decline as veteran pilots were killed faster than replacements could gain comparable experience, creating a downward spiral of declining effectiveness. By late 1944, average experience levels for American carrier fighter pilots exceeded 300 flight hours, including extensive combat time. Japanese carrier pilots often entered combat with barely 100 flight hours and minimal combat training, making them easy prey for experienced American pilots flying superior aircraft. The captured Hellcat's contribution to this disparity was indirect but real. The intelligence gathered from examining the aircraft helped Japanese commanders understand the scale of disadvantages they faced, but provided no practical solutions. Understanding that American fighters were superior did not make Japanese fighters more effective. Recognizing that American engines produced twice the horsepower did not enable Japanese industry to manufacture comparable power plants. The broader lesson from the captured Hellcat story extends beyond World War II specifics to fundamental questions about technology, industrial capacity, and military effectiveness. Superior technology matters enormously in warfare, but only when supported by the industrial capacity to produce it in meaningful quantities, the training infrastructure to employ it effectively, and the logistical systems to maintain it in operational condition. Japan had demonstrated in 1941 and early 1942 that superior training and tactics could overcome some technological disadvantages. Japanese pilots flying Zeros had dominated opponents flying aircraft with comparable or even superior paper specifications through better training, better tactics, and better understanding of their aircraft's capabilities. But by 1944, American forces had closed the training gap, developed tactics optimized for their aircraft's strengths, and deployed fighters that exceeded Japanese aircraft in nearly every performance category. The combination proved overwhelming. Japanese pilots might fight with extraordinary courage and determination, but courage could not overcome the fundamental disadvantages they faced in aircraft: performance, numerical strength, and pilot protection. The captured Hellcat examined at Yokosuka symbolized these disadvantages, demonstrating in tangible form the technical gap that separated Japanese and American aviation by mid-war. The Hellcat's massive engine became almost legendary among Japanese aviation personnel, who learned about the captured aircraft through official reports and unofficial accounts. 2,000 horsepower seemed an almost fantastic figure to engineers and pilots accustomed to engines producing half that power. Some Japanese engineers reportedly wondered whether such an engine could even be real, whether American intelligence might have deliberately fed false specifications to demoralize Japanese forces. But the physical presence of the captured aircraft at Yokosuka eliminated any possibility of dismissing the reports as propaganda. Engineers could see the enormous R-2800 with their own eyes, could measure its dimensions, could examine its internal construction. The engine was real, and it represented American engineering and manufacturing capability that Japan could not match. In the final months of the war, as American bombers ranged freely over Japanese cities and American carriers operated within sight of the Japanese home islands, the captured Hellcat at Yokosuka stood as a silent testament to the inevitability of Japan's defeat. The intelligence it had provided changed nothing strategically. Japanese engineers had learned every technical detail of American fighter design, had measured every component, had understood the design philosophy that created such a formidable weapon. But understanding could not overcome industrial reality. Japanese aircraft designers attempted to incorporate lessons learned from the Hellcat into new fighter projects during 1944 and early 1945. The Kawanishi N-1K2J Shidenkai represented perhaps the most successful attempt, featuring a powerful engine, heavy armament, and improved protection compared to earlier Japanese fighters. The aircraft could fight Hellcats on relatively equal terms when flown by experienced pilots, but production never exceeded 400 aircraft, far too few to influence the war's outcome. The fundamental problem remained unsolvable. Japan lacked the industrial capacity to produce high-powered engines in quantity, lacked the strategic materials necessary for robust airframe construction, and lacked the fuel to train pilots adequately. Examining the captured Hellcat had revealed these gaps with uncomfortable clarity, but revelation without remedy offered no strategic value. When American forces occupied Japan in September 1945, intelligence officers sought out Japanese aviation facilities to document what had been captured and studied during the war. At Yokosuka, they found extensive documentation of the Hellcat examination, including detailed technical drawings, performance analyses, and engineering reports. These documents revealed how thoroughly Japanese engineers had studied the aircraft and how little practical benefit they had gained from that knowledge. The American intelligence assessment concluded that while Japanese engineers had demonstrated considerable technical sophistication in their evaluation of the captured Hellcat, the knowledge gained had not influenced Japanese aircraft development in any meaningful way. The gap between understanding American technical achievements and replicating them proved insurmountable given Japan's resource constraints and industrial limitations. One American intelligence officer wrote in his report that the Japanese examination of the Hellcat resembled a medieval craftsman studying an industrial lathe, capable of appreciating the sophistication and recognizing the superiority, but utterly unable to reproduce it with available tools and knowledge. The comparison was perhaps harsh, but captured the essential truth that technical understanding without industrial capability provided no practical advantage. The story of the captured Hellcat represents a footnote in the broader narrative of the Pacific War, less dramatic than major battles, but revealing in its own way. Japanese forces captured and studied an example of the fighter that would help destroy Japanese naval aviation, learned all its secrets, understood its superiority, and could do nothing to counter it effectively. The 2,000 horsepower R-2800 engine that impressed Japanese engineers so profoundly represented more than just mechanical engineering achievement. It symbolized American industrial might, the ability to design, manufacture, and maintain complex machinery in quantities that overwhelmed opponents. By war's end, Pratt Whitney had produced over 125,000 R-2800 engines, powering not just Hellcats but also Corsairs, Thunderbolts, and numerous other aircraft types. Japanese engine production across all types and manufacturers barely exceeded 70,000 units for the entire war. Even if Japanese engineers had fully understood how to design an engine comparable to the R-2800, which they did not, Japanese industry lacked the capacity to manufacture such engines in meaningful quantities while maintaining quality standards necessary for reliable operation. The captured Hellcat examination thus confirmed what some Japanese leaders had feared from the beginning, that war with America meant conflict with an opponent possessing overwhelming industrial advantages that would eventually prove decisive regardless of initial tactical successes or fighting spirit. Admiral Isoroku Yamamoto, who had planned the Pearl Harbor attack, had warned before the war that Japan might achieve early victories, but could not win a protracted conflict against American industrial power. The captured Hellcat, examined 3 years into the war, provided concrete evidence supporting Yamamoto's prescient assessment. The admiral himself had been killed in April 1943, shot down by American fighters, never seeing the final proof of his warnings. The Hellcat went on to compile the most successful combat record of any American fighter in World War II, destroying over 5,000 enemy aircraft with a kill ratio of 19-1. More than 12,000 were produced in just 37 months. The type served through war's end and into the early post-war period before being retired in favor of jets and more advanced propeller fighters. The captured example at Yokosuka, Bureau number 08742, was scrapped in late 1945 or early 1946, its intelligence value exhausted and its historical significance unrecognized. No photographs of the captured aircraft in Japanese markings are known to survive, though detailed technical drawings and analysis reports remained in archives. Ensign Joseph Farnsworth, whose forced landing had provided the Japanese with their prize, returned home and lived a quiet civilian life. He rarely discussed his brief combat experience or his time as a prisoner of war. When asked about his wartime service years later, he would mention only that he had flown Hellcats and been shot down, omitting the detail that his aircraft had been captured and studied by Japanese engineers. The Japanese engineers and test pilots who examined the captured Hellcat dispersed after the war. Some continued working in aviation, helping rebuild Japan's aerospace industry during the post-war decades. Others left aviation entirely, pursuing different careers in a transformed Japan. Few spoke publicly about their wartime work examining captured American aircraft, the memories perhaps too painful, the lessons too obvious. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.